So what is the threshold frequency or the threshold energy? It is nothing but a minimum amount of energy possessed by the molecules in order to form a product. At the temperature T, the fraction of molecule possess the kinetic energy greater than or equal to the activation energy and capable of forming the effective coefficient. We all know that the rate of a chemical reaction is significantly affected towards a change in temperature. Hello my dear students, a warm welcome you all. Myself is Purnima, lecturer in Department of Chemistry at Vidhyaashram Pre-University College, Temple of Excellence, Mysuru. My dear students, in our last discussion, we were dealing with the unit called Chemical Kinetics. Under that, we have discussed about the half-life of a reaction, and also we talk about the pseudo first order reaction and overall view of the zero order and the first order reactions, and also we have discussed about the few numericals. Today, let us move on to the next topic of this unit about the temperature dependence of the rate of the reaction. And also we are going to understand about the Arrhenius equation, and we are going to understand what is an activation energy and qualitative increasing in reaction rate with a temperature. How does it takes place? Let us understand in this session. So firstly, we will discuss the temperature dependence of the rate of the reaction. We all know that the rate of a chemical reaction is significantly affected towards a change in temperature. As we increase the temperature, the rate of the reaction which is also get increased. Is it right? Yes. It will be significantly affected by the change in temperature. For the most of the chemical reaction, rate increases with increasing in a temperature. When you increase the temperature, the rate of the reaction which is also get increased. That is mainly because of the temperature coefficient. It is nothing but a ratio of specific rate constant of a reaction at a two different temperature differs by 10 degrees Celsius, known as temperature coefficient. So what is the temperature coefficient? It is a ratio of a rate constant at a two different temperature with the 10-degree raise in temperature. Then only we can say it is a temperature coefficient. Remember, it is a rate constant at a two different temperature with a 10-degree raise in temperature. Usually, it becomes double for each 10 raise in a temperature. For example, if I write the temperature raise will be around 40 degree Celsius and 30 degree Celsius, and the temperature coefficient can be obtained by dividing these two degrees, and you will get the temperature coefficient. Like this, only the 10-degree raise in temperature, which is known as temperature coefficient, and it is always double for the 10-degree raise in temperature. Next, to understand this temperature coefficient, Arrhenius gave an equation. Let us see what does that equation tell about it. So according to the Arrhenius, the reaction rate constant are directly proportional to the e to the power of minus Ea by RT at a given temperature T. According to him, so the rate constant K is directly proportional to the e to the power of minus Ea by RT. Is it right? In order to remove this proportionality constant, he put a new symbol called as A, and here A represents the Arrhenius equation. So what does the Arrhenius equation tells that? The rate constant is directly proportional to the e to the power of minus Ea by RT. Then what is that K? Already we know that K is the rate constant, A is the Arrhenius equation, and it is the Arrhenius constant we can say, and EA is nothing but the activation energy. EA is the activation energy. T is the temperature and R is a gas constant. Now, let us understand what is an activation energy and how does it can be defined. Let us see now. Okay. So, activation energy is a minimum energy required for the reactant to form a activated complex, and that is known as activation energy. It is a minimum energy required by the reactant to form an activated complex. Later you will see that how the reactant will form an activated complex by understanding the graph. Okay, and this can also be studied by using a formula, that is activation energy is known as is equal to threshold energy minus average energy possessed by the reactant. Okay, and threshold energy, it is nothing but a minimum amount of energy by the energy of the reactant molecules possessed to form a product upon the mutual collision. So what is the threshold frequency or the threshold energy? It is nothing but a minimum amount of energy possessed by the molecules in order to form a product. During the collision, it will produce that energy, that is said to be threshold energy. Now let us consider an example to understand what is an activation energy. I have considered H2 plus I2 give rise to 2Hi. So here you can say that there are 2H plus I2 giving rise to the intermediate product, and finally it is forming a 2Hi. Is it right? Here I have plotted the graph of potential energy versus reaction coordinate. Okay. So in this you can see that the H2 and I2 are nothing but a reactant. So during the reaction, we know that these H2 and I2, that is hydrogen and iodine, they collide with each other and they forms a product. But according to the Arrhenius, he tells that not all the reactant which undergo collision and forms a product, only when the reactant which are having some energy, that is known as threshold energy, it will form a product. How does it form? Let us understand. We know that here the hydrogen and the iodine which are in the reaction and they are nothing but a reactant. And here it is not forming a product. These molecules or these reactant, when they collide with each other, they forms a activated complex. They forms what? Activated complex during the collision. So when they forms an activated complex, they exhibit some energy that is known as threshold energy. That is said to be what? Threshold energy. When they gain this energy, this activated complex, again it forms into product. It forms what? Product. So this difference in energy, average energy of a molecules to form an activated complex, that is known as activation energy. That is known as what? Activation energy. So according to the Arrhenius, this reaction takes place only when the molecules of the hydrogen and molecules of the iodine are collide to form an unstable intermediate. Remember, this activated complex is always unstable. Why it is unstable? You can see here, there is a formation of the bond which is taking place and there is a breaking up of bond which is taking place, and here formation of the bond. Again, this is a breaking and this is a formation. So like this, on both the sides, a formation as well as a breaking which is taking place, and it is unstable. So once it forms a formation of the bond, it will give rise to the product. So it exits for very shorter time and it breaks to form molecules of hydrogen iodide, and energies required to form this intermediate are called as activated complex, and that is known as activation energy. So what does it mean? Again, I am going to explain this. Here, Arrhenius, he took the example of hydrogen and iodine and he plot a graph of potential energy versus reaction coordinate. At the beginning, he took the example of hydrogen and iodine. When these two reactants, when they collide, usually they are having some average energy. When they started colliding with each other, during this process, it will form a activated complex. When it reaches to the activated complex, it will gain some energy that is said to be threshold energy. The differences between these two, that is, the energy is required to form activated energy to the original position, that is said to be activation energy. When these activated complexes are formed, that is unstable and it will be lived for very short time and it will be converted into product. This is how, when you consider any two reactant in the reactions, only the few reactant which undergo collisions, it will form a product according to the Arrhenius. Hope you all understood that concept. Next, we will see how qualitative increasing in the reaction rate with the temperature happen. This relation was given by the Clerk, Maxwell and also with the Boltzmann. Okay, so all the molecules in the reacting species do not have the same kinetic energy, as we already know that. And this relationship was given by the Boltzmann along with the Maxwell. Use the statistics to predict the behavior of large number of molecules. According to them, what does it mean? The distribution of kinetic energy may be described by plotting the fraction of molecule with the given kinetic energy versus kinetic energy. So you can see that here they have plotted the fraction of molecule. What does it mean? So here Ne divided by Nt they have taken. Ne is nothing but a number of molecules with the energy E and Nt is nothing but the total number of molecules. Okay. For example, in the reaction, let us consider there are 100 molecules are there and activation energy of that particular molecules, say about for the N is 20, for A2 it is 30, for A3 it is again 30, for A4 again it is 20. For each molecules, activation energy will be different. So, according to him, fraction of molecules will be obtained by, suppose at A1, activation energy will be 20 divided by how many molecules are there? Number of molecules are there? 100. Like this, they have plotted the fraction of molecules on the y-axis and the kinetic energy on the x-axis. And they have got a plot like this, but at the center you can see that this line, this shows that most probable kinetic energy. So at this point, almost all the molecules, they have a highest kinetic energy, or we can say that the most probable kinetic energy. Next, the peak of the curve corresponding to the entire graph, which is known as most probable kinetic energy, that is, kinetic energy of that point in that molecules will be maximum. Okay, and the following figures which shows the energy distribution curve at a temperature T and T plus 10, such as T plus 10 is greater than T. At the temperature T, the fraction of molecule possess the kinetic energy greater than or equal to the activation energy and capable of forming the effective collision. So from this point, you can see that the highest peak in this entire curve shows that at this point, almost all the molecules, they can easily collide with each other because their kinetic energy will be increased. I'll raise the temperature and I'll plot the graph. What will be the differences? Now let us understand. Let us see, if I increase the temperature, what happens to the graph? Okay, as I increase the temperature from T to T plus 10, okay, the fraction of molecules having the kinetic energy are greater than the activation energy and it will be get increased. Later, thus effective collision of that molecules, that is also get increased and the rate of the reaction which is also get increased. Let us see with the graph. Here again I have plotted out the fraction of molecule versus kinetic energy, And you can see that as I increase the temperature from the T to T plus 10, you got a graph like this. But you can see that there is a shaded region in this part, and this shows that this is a part where the molecules will get the activation energy and forms an activated complex. Okay, and later it will be leads into the formation of product. But as I increase the temperature from T plus 10 degree, you will get a graph like this, and there is a larger area under this graph, the entire area as you can see now. The area under the graph which is increased, which means to say that they have got the extra activation energy, so that rate of the reactions which is obviously increased because we are increasing in the temperature. So this is how when you increase the temperature, the entire activation energy which has been gained by the collision molecules, that is also get increased. This is the area that shows the fraction of the additional molecules. Thus, we can say that an increase in the temperature increases the number of effective collision, resulting in increasing in the rate of the reaction. Increasing what? Rate of the reaction. As you increase the temperature, which increases the collision in the molecule, so that the rate of the reaction which is also get increased. Later, this can also be understood by two methods. The first one is graphical method, where the quantitative increase in the reaction rate with the temperature can be understood. Okay. So, first one is a graphical method. So, in the Arrhenius equation, we know that the factor e to the power minus Ea by RT corresponding to the fractional molecules that have a kinetic energy greater than Ea. So that is why I have written by taking the logarithm on both the sides of the equation. We know that from the Arrhenius equation, K is equal to A into e to the power of minus Ea by RT, where A is a Arrhenius constant. That is why I have plotted ln K versus 1 divided by T. So, you will get a slope like this, and from this we can easily say that at this point it has intercept which gives the values of ln A, whereas the slope which gives rise to the values of minus Ea by R. This is how the straight line can be easily get when we take the logarithm for the Arrhenius equation, and this is a graphical method. So, the slope of these lines are equal to the minus Ea by R and intercepts which give us to the ln A. Hence, by measuring the slope of the line, the activation energy Ea can be calculated. By measuring what? The slope of that curve, we can easily measure the activation energy of that particular compound. This is how we can graphically understand that how the Arrhenius equations, which is also related to the temperature. Next, with the rate constant method, let us understand. At a temperature T1, we know that I am changing the temperature now. Arrhenius equation is K is equal to A into e to the power of minus Ea by RT. Okay. I am taking the log on both the sides. Now it can be defined as ln K1 is equal to minus Ea by R T1 plus ln A. At a temperature T2, ln K2 which is equal to minus Ea by R T2 plus ln A. Here A is nothing but the Arrhenius constant, and we all know that K1 and K2 are nothing but a rate constant, and the T1 and T2 are nothing but a raise in temperature, that is from T1 to T2. Subtracting the equation 2 with the equation 1. What is the equation 2? That is ln K2 minus ln K1 is equal to minus EA by RT ln plus ln A minus EA by RT plus ln A. This is a thing. And you can directly write this as minus EA by RT plus ln A minus into minus plus. Is it right? So it is EA by RT plus into minus, it is minus ln A. This is the thing we will obtain. Now I'll cancel out plus ln A with the minus ln A, and I can write it as ln K2 minus ln K1 is given out by minus EA by RT2. These are the temperature T1 and temperature T2. Now I am taking out the K2 and K1 constant, so that ln K2 divided by K1, which is equal to EA and R are constant here. So EA and R will be taken outside. So EA by R, which is equal to, which is EA by R into 1 divided by T1 minus 1 divided by T2, because the temperature differences are more. So if I take the ln and if I convert it into logarithm, now log K2 divided by K1 is equal to 2.303. We have to multiply it with the 2.303 if it is there in the ln, as we know that. So EA divided by 2.303 into R into 1 divided by T1 minus 1 divided by T2. Or finally you can say that log K2 divided by K1, which is equal to EA divided by 2.303 into R into T2 minus T1 divided by T1 and T2. This is the LCM which I have taken. So this is the equation which we are using to calculate the rate constant along with the difference in temperature if they have given the activation energy along with the R, that is the gas constant. This is how the rate constant method can be used to calculate the difference in temperature. So by this, in the next class, we are going to discuss with the effect of catalyst along with the collision theory of chemical reaction. So what I have discussed in this session, again it is very important for the examination point of view. Have a look on it and try to work out. Wherever you are not understanding, pause the video and write once again and understand the video. We'll meet you in the next session. Till then, take care and be safe. Thank you.